So, just to kind of recap, I'm going to divide this up into three, hopefully, maybe 15, 10-minute long presentations. And the first thing I want to talk about is what momentum is, how we describe it, and some of the properties that momentum depends on. So, first off, the definition for momentum is how hard it is to stop something from moving. And the two things that really determine that are mass and velocity. And we did something in class, if you remember, where we had Vince Wilfork running at you, or Usain Bolt running at you, or Julian Edelman. And we decided that Usain Bolt, with his mass and his velocity coming at you, would be the hardest thing to stop. And that's kind of what really determines momentum. You know, it's not just the fact that something is massive, but it's also the fact that something's going very quickly that makes it have a lot of momentum. And that momentum can really do a lot of damage. So those are the two things that really depend on it. And we actually, if we want the equation for momentum, it is momentum equals mass times velocity. And we actually sometimes will put a little arrow over it. It doesn't really matter for our sake. But when you get to college, the big thing about momentum is it is a vector as opposed to a scalar. And what a vector really determines, or what it means to be a vector, at least in the case of momentum, is that the direction for the momentum is given by the sign. So if it's a positive sign, it's either going forward, or to the right, or if it's a negative sign in front of it, it is either going backwards or to the left. L-E-F-T. So these are the two big deals with it, and just to give you a little couch to talk about this, you could say we got a car that's 1,000 kilograms, and it's traveling at, let's say, 25 meters per second to the right, so that would be a positive 25 meters per second. We would say that that car has 25,000 kilogram meters per second of momentum, and that's the strange unit for momentum, but kilogram meters per second. And if we change that to negative 25, and we had the same car now this time going to the left, it would be negative 25,000 kilogram meters per second. So that's basically how you calculate momentum, and it's interesting in as much as we can sort of, well, there's the equation, P equals mv. And, you can sort of get an idea for the bigger the momentum of something is, the harder it is to stop. And the smaller the momentum of something you're dealing with, the easier it is to stop. So that's why, you're dealing with your car going, let's see, here's my car / UFO, because I can't draw. Let's say the car is going this way with a velocity of 20 meters per second, let's say. And then we got a little fly here. It's a fly. And the car goes, and what do you think is going to happen to the little fly? It's probably going to be a bad day for the little fly. And the reason for that is because the fly has such a very small mass, and the car has a very big mass, and the fly might be traveling, but it's not traveling very fast, so you're dealing with a very small mass times a small velocity for the fly, and you're dealing with a big mass and a big velocity for the car. The fact of the matter is the mass times velocity of the fly isn't really going to be able to stop the mass times velocity of the car. So the fly ends up on the hood of your car or the windshield of your car, kind of splattered. But had this been a much bigger fly, or a fly that was going much faster, it might have been able to actually do some damage to your windshield. Maybe if if you ever had a chip in windshield caused from a pebble, and the pebble has a very small mass, but maybe it's going fast enough, or it's hard enough. We can talk about that later, where the collision doesn't really cause damage to the fly; it causes damage to your windshield. But we'll get into that later on. We'll talk about elastic and normal inelastic collisions. So, but the basic story here is the bigger the mass and velocity, the more likely you are to plow through something that has a smaller mass and velocity. I don't know why that just disappeared, so let's bring it back. So, there you go. Going on, I want to talk to you about impulse, which is something that it's technically a push or a pull for time, and it's given to us by the equation J equals F delta T. Impulse is J, force is force in newtons, change in time is exactly what it sounds like, a time. If I push this bottle of cranberry lime soda water for 5 seconds, we would multiply the amount of force I'm applying times the change in time for the 5 seconds. So what we would end up here is Newton seconds, but since newtons are actually kilogram meters per second squared times seconds, those cancel out, and we're left with, once again, kilogram meters per second, which is the same unit, ironically, as momentum. So why does this matter? Well, we could say, all right, I pushed Julian Edelman with a force of 5 newtons for 10 seconds. So I am actually imparting upon him 50 Newton seconds, or 50, as we just saw, kilogram meters per second on Julian. And that would mean he's going to change his momentum. So what some of the problems that we'll see relate impulse to a change in momentum. And typically when we change something's momentum, we're not changing the object's mass. So we get this equation here where J will cause a change in momentum. But typically, J, which stands for F delta T, we won't be changing the object's mass, so it's typically the mass times the change in velocity. And what that would mean is, in reality, here's me, and let's say I push Julian. So let's say I somehow, some way push him, and I push Julian Edelman for that 50 kilogram meters per second from back here. That means Julian Edelman's momentum is going to change. I'm not going to cause his arm to fall off. I'm not going to cause his leg to fall off. So his mass is going to stay the same. But that momentum change, so let's say again that's 50 kilogram meters per second, will cause his mass, whatever it is, to change its velocity. So let's say Julian has a mass of, I don't know, 100 kilograms. So I'm going to lose the units just to make the numbers easier to see. Let's say Julian's mass is 100 kilograms. His velocity will change then by the amount of momentum that I caused to change. And you can figure that out by dividing both sides by 100. And his change in velocity would then be 50 over 100 is a half a meter per second, actually, just by me pushing him with that 50 kilogram meters per second, or 5 newtons for how long was it? 10 seconds? Yeah, 5 newtons for 10 seconds. So if I could push Julian Edelman with 5 newtons of force for a whole 10 seconds, I could actually cause him to either speed up or slow down by a half a meter per second. Now, what's going to determine whether he speeds up or slows down is if he's moving with the push. So if I'm pushing him to the right, he would speed up by a half a meter per second. Or if he was moving to the left, he would slow down by a half a meter per second, because the push and the force would be acting against Julian Edelman's momentum. So that's kind of, and that's sort of the Cliff's Notes version for this. And you'll see some formulas and some problems that will deal with F delta T equals M delta V. But that sort of leads us into the big third thing, and I just want to see how much time I'm going into here. That is not correct. That's the one I want. The big way that we change momentum and we impart impulse is we actually have something called a collision. And this is going to sort of wrap up the introduction to momentum. And there are 3 types of collisions: 1, 2, and 3. The first type of collision is called a perfect elastic collision, and that happens where Ke is conserved. and momentum is conserved. And this is perfect elastic. I almost want you to think about a super ball. And if you remember from class, we did the lab where we dropped the super ball and we noticed that it didn't come all the way back up because it lost some energy when it hit the floor. So when we're dealing with any collision, we're talking about two objects hitting each other. And in the perfect elastic collision, it would almost be like that example where we dropped the ball and it came almost all the way back up. But in a perfect elastic collision, it would come all the way back up to where we dropped it from. And the reason that would happen is because none of the energy from the ball would get lost in the sound or the deformation of the ball. Remember how we talked about the ball actually gets dented or squished, and that causes internal friction, and that friction causes heat to be lost. Well, the more squish you get, the more friction there is lost, or the more friction there is, the more friction there is, the more heat is lost. So you get a case where one of these balls deforms a lot when it hits the ground, and it loses a lot of energy, and instead of coming all the way back up, it might only come up a little bit. A perfect elastic collision, that doesn't happen. So if the ball starts from here and falls all the way back down to the floor, and there's the floor, the ball would then come all the way back up to where it started. Not above it, not below it, but exactly where it started. And a perfect elastic collision will never happen. It sort of can in ideal gases and atoms hitting each other and conserving all of their kinetic energy, but for what we deal with on the macroscopic scale, we'll never see one of these happen. But it's a good example to talk about because then we can think about some of these other types of collisions where momentum, I'll get into the second one. We call the second one a normal inelastic collision. And the normal inelastic, you lose kinetic energy, so Ke is not conserved. But you do keep your momentum. Momentum is conserved. And what that would be is, here's the floor again, here's the ball, drops down, hits the ground, and only comes up maybe halfway or 3/4 of the way, but never back to quite where you started from. And the reason for that, again, is because we lose energy in the collision. The third collision that we like to talk about is a perfectly, I can't spell, perfect, I'm just going to erase this, perfect inelastic collision. And these are where the maximum Ke is lost. And that happens because there's a lot of energy lost in the collision. You're talking about maybe a clay ball that when you drop it on the ground, it deforms so much, not a baked clay ball, but like a Play-Doh ball that you can still play with. You drop it on the floor and it doesn't bounce up because it just kind of goes splat on the ground. And it loses a lot of energy because it takes a lot of energy to change that ball from being nice and round to sort of a flat pancake. So criteria one is that the kinetic energy is lost, the maximum amount of it is lost. The second criteria is that, again, momentum is conserved. And then the third criteria, and this is just for me, because I like to think about this, two objects go in, only one comes out. So if you're thinking about this clay ball, it used to be a nice ball, it falls down to the ground, and yes, I know, it falls down to the ground and becomes sort of a flat pancake. And it doesn't come back up anymore. So you have lost essentially all the kinetic energy you can lose, and you are now one with the floor. A lot of times we'll talk about maybe balls going in opposite directions, and then they will, after the collision, essentially become one ball. The two masses of these things will combine. So that's sort of the introduction to momentum. The three types of collisions, the two equations that we really need to worry about. But I want you to pay attention to one more thing, and that is the fact that in all three types of collisions, momentum is always conserved. And what that really means for us is that the initial momentum, Pi, initial momentum total will always equal PF total, or the final momentum total. And you'll see this written different, P total F or P total I, and I even go back writing it one way or the other. But basically, the name of the game is the momentum you have in the beginning, the momentum you have before a collision, will always equal the momentum you have after a collision, no matter what. And we can do this because, again, momentum is a vector. So we can add negative momentums. We can add positive momentums. And that's really where this all starts to get into itself when we start talking about one-dimensional collisions. So I hope this kind of gives you a good place to start. It's what we've talked about in class 2 weeks ago. And what we've been doing the past week has been going into what happens with these different types of collisions. But this is basically the beginning of it, and we'll get into some more in the next video. So with that, I'm going to do this.